All right, so we're skipping a few lessons here, moving on to lesson 8.7 out of your textbook. This is the only lesson we do out of chapter 8. Most textbooks put this lesson earlier in the book, and that is why Fort Scott requires that we do this lesson, because a lot of schools, when you go into Calc 2, you're expected to already know this. Some schools, you'll get there and you'll do it in Calc 2, so we do it just to cover our basis on that. But this is a limit lesson, but don't let that freak you out. This once you do this one, you'll kind of be like, why couldn't we have learned this in the beginning? Because this makes limits a lot easier. But you can't do this until you know how to find a derivative, and you can't find derivatives until you know how to do limits. So that's why this isn't put until after the limits you've already learned. Our success criteria is to use what's called L'Hopital's rule to find limits. He was a famous mathematician, French mathematician, that was this rule is named after. All right, so let's review what we know about limits a little bit already. If you recall back from our first chapter that we did on limits, when I did a limit like this, I would run into problems just using plain old substitution. Notice that if I replace x with infinity, a really crazy large number, all I'll end up with is infinity over infinity. And infinity over infinity, you would think, would equal 1. But not necessarily, because that doesn't mean these two numbers are clearly the same number. One of these infinities might be maybe this top number is larger, maybe the bottom number is larger. Clearly, by looking at this, we can see that the top number is larger, but this is what we call an indeterminate form. We can't really figure anything out from this. So we had learned back in chapter 1, when we do problems like this, we divided by the highest power of the denominator. So when we divided by the highest power of the denominator, we had something that looked like this, x cubed over x cubed. And then we had 3x cubed over x cubed. And then we had 1 over x cubed. And we said that if you did that these would cancel. And these would cancel and give you 1 and a 3. And then, so I have 3 over 1. And then this, we said, is basically a reciprocal function. And the reciprocal function, as you approach infinity, goes to 0. So we did the problem like that, and we ended up with an answer of 3 over 1, which is 3. So this comes out to be 3. But remember, when we plugged in the infinity, we got this. Infinity over infinity, which there is no way of obtaining a 3 from this. And what L'Hopital does is when you get something like this, he comes up with this new method to where you can do the derivative in another method, and we'll do that here in just a second. Here's another example of an indeterminate form. If I do this problem, remember limits can be separated. So if I were to do this as the limit as x approaches 0 for x times the limit of 1 over x as x approaches 0, if I plug 0 in here, I just get 0. If I plug 0 in here, I get 1 over 0. And if you have 1 over a number incredibly close to 0, remember that approaches infinity. So I come up with 0 times infinity. And most people would think that 0 times infinity would give you 0, because 0 times anything is 0. But if you go back to this original function and you think about it, you could simplify this. If you take x over 1 times 1 over x, you get x over x, which is just 1. So I know the limit of any constant is just itself. So I know the correct answer to this thing is 1. It can't be 0. So that's another great example of why this is considered an indeterminate form. This one's an indeterminate form. They can't be trusted to give you the actual limit. And there are several of those forms. Here's a page that you might want to reference back to or take a picture of that tells you all the trusted forms involving zeros and infinities and all the ones that can't be trusted. So if you substitute in and you get infinity plus infinity, no problem. Really big number plus really big number always equals really big number, and that's going to be infinity. Same with a negative large number and a negative large number. And here's one you probably wouldn't think a whole lot about. 0, if you ever get a 0 to the infinity power, that means a infinite number of zeros multiplied together. And guess what? It's still 0. That's not going to change. This one, 0 to the negative infinity, is like 1 over 0 to the infinity, and that's why it goes to infinity. Kind of like the reciprocal function backwards, I guess you could say. As you approach 0, it goes to infinity. So this would be approaching 0. So anyway, the point is all 4 of these can be trusted. They will always give you these answers no matter what. The ones that can't be trusted are the ones listed over here. For example, infinity minus infinity. Well, you don't know which one of the infinities is bigger, and you don't know by how much, so that can't really be trusted. You would think that 0 times anything would always equal 0, but we just proved on that previous slide that it didn't when you're talking about limits. So these 7 over here cannot be trusted forms to give you a limit. You can't just go, well, anything to the 0 power is 1, so you're going to assume this limit is 1. An infinite number of 1s multiplied together you would think would be 1, but that does not always give you the correct limit. So you never can trust these. And a guy by the name of L'Hopital has come up with a nice little rule that we can use to make limits easier whenever we get these forms. And that's on the next slide. And so L'Hopital's rule basically says this: if you have a limit of a rational function, rational just means you have some function in the numerator, some function in the denominator, and you have a limit as x approaches a, and you substitute that a in. If you do that, and you get 0 over 0 or infinity over infinity, then you can use this rule, which is called L'Hopital's rule. And it says that the limit of a rational function is equal to the limit of its individual derivatives. So I'm not talking quotient rule here. You wouldn't use the quotient rule, but you would simply take the derivative of the numerator, the derivative of the denominator, and then find the limit of that, and that limit will always come out the same as this limit, which is very helpful because taking derivatives makes power smaller. It makes it a lot easier to substitute in this a value. Now remember, you can only use this when you get 0 over 0 or infinity over infinity. You cannot use it when you get these other 5 forms. But if you do get any of these other 5 forms, it's possible a lot of times to transform them into a rational function so that you can get these. All right, so let's do some examples. Here's an example, and notice what happens when I plug in the 5. Notice this means the limit as x approaches 5 from the left-hand side. They have to put that there because if you do numbers on the right-hand side of 5, this is going to end up negative, and that would not be allowed. So, if I do plug in the number 5, notice what happens. I end up with a 0 over a 0, because 5 squared is 25. 25 minus 25 is 0. I have 0 over 0. Well, remember, anytime that happens, when you get 0 over 0 or infinity over infinity, you're allowed to use what's called L'Hopital's rule. And L'Hopital's rule says you can take the derivative of each of these individual functions and then take the limit, and it should give you the right answer. So I need to find the derivative of the numerator and the derivative of the denominator, and then take the limit as x approaches 5 from the left. So how do I do the derivative of this? Well, remember that can be written with a 1/2 power. So if I do a derivative of the numerator, first of all, I'm going to write my limit out here. If I do a derivative of this, the numerator, I'm going to get 1/2 times 25 minus x squared to the negative 1/2 power times the derivative of the inside, because it's more complicated than just an x. I have to use the chain rule there. So that's the derivative of my numerator. My denominator is super easy. The derivative of that is just 1. So now if I simplify that thing before I take the limit, which would be a great idea, let's see how it can simplify. This 2 can cancel with that 2. This thing can be shoved down to the denominator. So if I do that, I'm going to end up with the limit as x goes to 5 from the left of negative 1 in the numerator, and I guess I have an x too, don't I? I should just put x, negative x over the square root of 25 minus x squared. So left the x in the numerator and the negative sign, shoved all this down to the denominator, switched the 1/2 power to a square root. And so now, if you plug in the 5, what happens? Let's try it again. Plug in the 5. I'm going to end up with... Alright, so now if you plug in that 5, when you plug 5 into here, you're going to get negative 5. When you plug 5 into here, you're going to get 0. And remember, these are really limits. So it means what is happening to this as x gets incredibly close to 5. So if you put in a 5 in there exactly, you get a 0. But as you're getting incredibly close to 5, then it's giving you a number that's crazy close to 0. So think of numbers that are crazy close to 0, like maybe 1 over 1,000,000 or 100,000. That would be incredibly close to 0. So remember, this is a limit as x is approaching 5 from the left-hand side. So as you're approaching 5 from the left-hand side, this quantity right here is getting insanely small. So rather than put a 0 there, think about it as 1 over infinity or 1 over an insanely large number. And so then if I were to flip and multiply, I would get an insanely small or large negative number, however you want to think about it, and therefore my answer would be negative infinity. So maybe here I should put 1 over infinity, because that would be incredibly close to 0. And then if I were to flip and multiply, that would be negative 5 times that crazy large number, which would come out to be a crazy large number. So the answer is negative infinity, because you've got this negative here to begin with. And to verify that for you, I've got the graph on the next slide. You can look, this is the graph of that function on your graphing calculator. Here is 5, and as I approach 5 from the left-hand side, what's happening to the graph? It's going to negative infinity. And so this is not an indeterminate form, that 5 over a number crazy small to 0. We had things like that in chapter 1. All right, so our next example on this one, let's say you're going to plug in 0. So let's see what happens if we plug in a 0. If I plug in 0, I'm going to get e to the 0 minus 1, and then I'm going to distribute this negative over here. That's minus x, so that would be minus a 0 all over 0. And, of course, anything to the 0 power is 1, so on the top I have 1 minus 1, which is 0. On the bottom I have 0. So I have 0 over 0. Remember in the last problem I had 0 over 0 as well. 0 over 0 or infinity over infinity means that I get to use L'Hopital's rule. So I can use L'Hopital's rule by taking the derivative of the numerator and the derivative of the denominator. So now I'm doing the limit as x approaches 0, and the derivative of e to the x is simply e to the x. And the derivative of negative 1 would be 0, so I don't worry about that. The derivative of negative x, that's a negative x if you distribute, would be a negative 1. And the derivative of x would be 1. So now I have that, and now if I plug in 0, I simply get e to the 0 minus 1 over 1, and anything to the 0 power is 1, so I have 1 minus 1 over 1, which is 0 over 1, which is 0. So the limit of this function right here was found by taking the limit of its derivative, which gives you the exact same function. So my answer for that problem comes out to be 0. All right, example 3, and if you remember these examples from chapter 2 on limits, these were the ones where we did something like this. There was a theorem as the limit as x approached 0 for sine of something over x. Oh, it was sine of x over x. That always came out to be a 1. And so the way we worked this problem was we multiplied the numerator and the denominator by a 1 over x, and that would give us something that looked like this. Once again, just refreshing your memory as to how we used to do it. And now I need a 4 here in order to be able to use the theorem, so that means I got to put a 4 here also. I need a 9 here, so I have to put a 9 here. And now that limit goes to 1, that limit goes to 1, and I end up with 4 9s as my answer. So what would this look like with L'Hopital's rule? Well, in L'Hopital's rule, we plug in the 0. So if I plug in the 0, I'm going to have sine of 0 over sine of 0. And that means, what's the y value when you're at 0 degrees? Well, that's 0. So once again, I get a 0 over 0, and 0 over 0 means I can use L'Hopital's rule. So what L'Hopital's rule says is that you can go back to this original rational function, take the derivative of the numerator and the derivative of the denominator, and then plug in the 0 and see if it works. So let's do that. And remember that the derivative of sine is cosine. So I have cosine of 4x, and I have to multiply by 4 because the derivative of that is 4. And in the denominator, the derivative of sine is still cosine, so I have cosine of 9x times 9. And so now when you plug in the 0, I plug in the 0, and I get 4 times the cosine of 0 over 9 times the cosine of 0. And the cosine of 0 means, what's the x value when you're at 0 degrees or 0 radians? Well, the x value at 0 is a 1. So I end up with 4 times 1 and 9 times 1, which is simply 4 9ths. Same thing we got doing it the old way, but the algebra is a little easier. All right, example 4. So if you look at this one, this is one where we would have divided by the highest power of the denominator back in chapter 2. If you divide by the highest power of the denominator, that would be an x squared. You would divide every term by. L'Hopital's rule, you would plug in the infinity. If you plug infinity into the numerator, you will get infinity. If you plug infinity into the denominator, you will get infinity. And now you have infinity over infinity, and that's the other case where you're allowed to use L'Hopital's rule. And L'Hopital's rule says take the derivative of the numerator and the denominator. So if I do that, I will have the limit as x goes to infinity for 3x squared. That's the derivative of the numerator. The denominator comes out 2x plus 2. All right, now we'll plug in the infinity again. Notice when I do that, I get infinity over infinity again. So that just means that you're allowed to use L'Hopital's rule again. So if I use L'Hopital's rule again and take the derivative of the numerator and the denominator, I'm going to get 6x in the numerator and 2 in the denominator, right? And 6 divided by 2 is simply 3x. So now all I got to do is substitute the infinity in here. 3 times a really large number is still a really large number, so my answer to that problem is infinity. All right, example 6. Here's another case where we're going to plug this infinity in, and we may not know for sure what ln x to the fourth looks like on a graph, but I do know what ln infinity to the fourth power would be another infinity. And what is, I know the graph of ln looks like this. So as x goes to infinity, ln is going to go to infinity as well. So this is going to be another example of infinity over infinity. And anytime I get infinity over infinity, I get to use L'Hopital's rule. And so L'Hopital's rule says take the derivative of the numerator and the denominator. So remember, the derivative of an ln is a 1 over x, or in this case, an x to the fourth. And since it's more complicated than just an x, I have to multiply times the derivative of x to the fourth, which is 4x cubed. And then in my denominator, the derivative of x cubed is simply 3x squared. All right, so now let's see, what can we do to simplify this? I can multiply my two numerators together, 4x cubed over x to the fourth, and then I could flip and multiply my denominator. to get that all simplified down. So let's see, basically I have a 4 on top, a 3 on the bottom, I have 6 x's on bottom and 3 x's on top. So if I simplify that, I'll end up with a limit as x approaches infinity of 4 thirds with an x cubed in my denominator. And so basically this is a reciprocal function. Anytime you have just an x on the bottom with an odd power, that's a reciprocal function. So what happens to a reciprocal function as x approaches infinity? As x approaches infinity, a reciprocal function will go to 0. And so this is just a compression stretch number out here. So the answer to this thing is 0. Alright, so I'm going to have to plug in an arctangent on this one. Plugging 0 into the numerator and the denominator, I'll get a 0 in the numerator. Arctangent, that means inverse tangent. 2 times 0 would be 0. So remember, tangent references slope. So this means where in the coffee cup handle do I have a slope of 0? Well, add 0. So there we go. There's another 0 over 0 off to using L'Hopital's rule. So derivative of the numerator would be 1. Now what's the derivative of an arctangent? You may have to grab your math Bible there to refresh your memory on the derivative for an inverse tangent. It's on page 4 at the bottom, and the derivative is 1 over 1 plus x squared. 1 over 1 plus x squared. Now remember, I don't have an x, I have a 2x, so it's 2x squared, and then I have to multiply times the derivative of 2x, which is 2. And so now I have that, so if I simply flip and multiply, I will end up with 1 plus that 2x squared, which is a 4x squared, all over 2. It just flips over that denominator. So now if I plug in 0, plug in your 0 now, and you'll end up with 1 over 2, which is 1/2. And that would be your answer. All right, moving on to those other indeterminate forms. So far, all we've talked about were, if we go all the way back to that one slide, this slide, so far we've only done problems that dealt with these two. Now we're going to do problems that deal with these 5. These 5 indeterminate forms here. So let's go to this example and see what happens when I plug in an infinity. If I plug an infinity into this and I plug an infinity into this, remember that this is an exponential function. The original parent function for the exponential looks like this. But I have a negative on my x, which happens to flip it over the y-axis. It's a y-axis reflection, so now it looks like that. And so what would happen on this function as x approaches infinity? As x is approaching infinity, then that's going to go to 0. So this comes out to be 0 times, and the square root of an insanely large number is still going to be insanely large, so I get 0 times infinity. And remember, 0 times infinity is not a form that can be trusted. So I have to do something to rearrange this thing so that maybe I can use L'Hopital's rule. So think about the fact that I have a negative on that e, on the exponent. So I could change that to the limit as x approaches infinity of square root x over e to the positive x, which simply just shoves that down. And maybe you would have thought to do that in the beginning, which is fine. Shove that down in the beginning and just skip through this part. But if I shove that down there, now I get infinity over, now I have the exponential. The exponent parent of the exponential looks like, this function right here looks like this. And as x goes to infinity, so does this. So now I have infinity over infinity. Well, how is that helpful? Now I get to use L'Hopital's rule. I can't just use L'Hopital's rule. I have to get it to either infinity over infinity or 0 over 0 to use L'Hopital's rule. All right, so now I'm going to take the derivative of each one of those. So if I do that, I will have the limit as x goes to infinity of 1/2 x to the negative 1/2 over e to the x. And if I simplify that, I end up with 1 over 2 square root x e to the x. So now if I plug in infinity, I get 1 over 2 times infinity times infinity, which really large number times really large number is still a really large number, so I basically get 1 over infinity, and that's like 1 over a million, which is crazy close to 0. So my answer to that problem comes out to be 0. All right, example 8. So on this one, if I plug the number 1 into both of these, once again they're saying from the right-hand side, probably because I would have an asymptote here, and this would come out 0 if I were exactly 1, or if I was on the, could be that I have, this problem doesn't exist on the left side of 1. So anyway, if you plug in 1, you have 1. All right, so I went and grabbed the graph of 1 over ln x so you could see what it looks like. It looks very similar to the graph of this. We know what the graph of this is. This is simply the reciprocal function that has been shifted 1 to the right. So if you shift the reciprocal function 1 to the right, and they're asking you what's happening as x approaches 1 from the right-hand side. Well, this is the 1 right here on this graph. So in both cases, the graph approaches infinity as you approach 1 from the right-hand side. So this comes out infinity minus infinity, which is a indeterminate form. You can't say that negative or infinity minus infinity equals anything. But what we can do is try and get this in a format so that we could use L'Hopital's rule. So what could I do with this thing to turn it into a rational function? To turn it into a rational function, I probably would want to do a common denominator. So if I find a common denominator for those two, that would be ln x times 1 minus x. So that means 1 minus x for my numerator there, minus ln x, all over x minus 1 times ln of x. So nothing there can be simplified. So now what happens when I plug in a 1? If I plug in a 1, I get a 1 minus 1 minus ln of 1. Remember that ln of 1 would mean what power would you put on an e to get a 1, and that would be a 0. And then for my denominator, I'm going to have 1 minus 1 times 0. So you can see I end up with 0 over 0, which means that I get to now use L'Hopital's rule. And to do L'Hopital's rule, I take the derivative of the numerator and the derivative of the denominator. So for my numerator, the derivative will be 1. I don't worry about the constant because that goes away. And then the derivative of an ln is a 1 over x. So that's what I get for my numerator. Now my denominator is going to be a little bit more complicated because I have a product rule there. So I am going to have to do a u and a v. So I'll do that up here. Let's let u equal x minus 1 and v equal ln x. So u prime is going to be 1 and v prime is going to be 1 over x. So now if I do u prime v plus v prime u, I will end up with ln of x, that's my u prime v, plus v prime times u would be x minus 1 over x. That's simply multiplying these two together. So now, how am I going to simplify that? Well, probably want to multiply both numerator and denominator by an x so that you can get rid of that fraction within a fraction. So if I take numerator and denominator times an x, I'm going to end up with x minus 1 over x ln x plus x minus 1. And so now we'll try substituting in again. So if I substitute 1 in, let's see what happens. Alright, so when you plug 1 into this thing, notice what happens. You get 1 minus 1 over 1 times 0 minus 1 minus, or plus 1 minus 1. Guess what? We get 0 over 0 again, and here we go, L'Hopital's rule one more time. So this one's a little bit complicated because we have to use it multiple times. Alright, so we get to take the derivative again. So taking the derivative of this thing right here. So the derivative of the numerator will be easy. Limit as x approaches 1 from the right-hand side of 1 over, here's my product rule again, and it's the exact same one I had up. Is it? Close, not quite the same. So this time my u will be in x and my v will be in ln x. So if I simply go back and replace this with just an x, u is equal to x, which means u prime is a 1. So now I've got to take u prime times v, which is ln x, plus v prime times u. If you take v prime times u, you get x over x, which is just 1. So I get a plus 1. And now I have to take the derivative of this, which is another 1. So now I end up with a 1 over ln of x plus 2, basically. And now when I plug in the 1, I get 1 over, remember that the ln of 1 is 0, and now I end up with 1/2 as my answer. Alright, now we're going to do an example of when you have a variable in your base and a variable in your exponent. So that is where you're going to run into these three cases here. Anytime you have a variable in the base and in the power, you could possibly encounter any of these three, and we'll do a couple of those. So if I were to plug in infinity into this, notice I will get 1 plus, think about what 1 over an insanely large number means. That means you're crazy close to 0, so that would approach 0. And then put an infinity there, so I end up with 1 to the infinity power, which is one of those indeterminate forms. I cannot use it. I can't use L'Hopital's rule yet, because to use L'Hopital's rule I must have 0 over 0 or infinity over infinity. Well, if you remember back in derivatives, it helped a lot if we could incorporate an ln here. But notice I don't have a y equals out here or anything like that. So what I'm going to do, remember that when you have an e to the ln of x, if you remember our rules for logarithms, the e and the ln cancel each other out, and I'm left with just an x. So anytime I have something, I can put an e to the ln, it cancels it out and means the same thing. So that's what I'm going to do here. I am going to incorporate an e to the ln. So limit as x goes to infinity of e to the ln of 1 plus 1 over x to the x power. So this is equivalent to this because the e and the ln cancel out. Okay, so that is equivalent to what I have up here. Now the purpose for doing that is now I can take this x and move it out in front of the ln. So now I've got e to the x times ln of 1 plus 1 over x. Simply move that out in front. Now this e, I'm going to continue to work this problem, and all the work is going to be done in the exponent. So this e, theoretically, I'm just going to kind of leave it off and bring it back at the very end. So at the very end, I'll put an e back in for my answer. Or if you'd rather work the whole problem with this e in here, you definitely could. So now if I go through and I plug in the infinity, I'm going to end up with a infinity. I'm just kind of setting that e aside for now, plugging the infinity in for x, and then I'll have ln of 1 plus 1 over infinity. Remember, 1 over infinity approaches 0, so that's like 1 plus 0, and ln of 1 is 0. So once again, I've got an undetermined form. Well, what can I do with that? How about I try to make it a fraction? So let's take this thing right here, x, just my power, x ln of 1 plus 1 over x, and let's rewrite that as ln of 1 plus 1 over x over 1 over x. So in other words, I'm taking this x and flipping it down here. In order to do that, I have to make it a 1 over x. Imagine if I were to take this and flip and multiply it. If I would flip and multiply this times this, I would have this again. So anytime I want to move that to the denominator, just make it a 1 over x. So now if I plug infinity in, I'm going to end up with 0 over 0, because I'll have ln 1 over 1 over infinity, which is crazy close to 0. So I have 0 over 0. So now I can use L'Hopital's rule. Now I can take the derivative of the numerator and the derivative of the denominator and work it from there. It takes a long time on this one just to get set up to even be able to use L'Hopital's rule. Alright, so if I use L'Hopital's rule, I am going to take the derivative of an ln, which is simply 1 over itself. So I'm going to have 1 over 1 plus 1 over x times the derivative of my denominator. The derivative of my denominator would be what? Remember that 1 over x is the same thing as x to the negative 1. So the derivative of x to the negative 1 would be a negative x to the negative 2, and that's what I have to multiply by. Multiplying by the derivative of my denominator, which would be a negative x to the negative 2 power. Okay, so that took care of this derivative right here. 1 over this times the derivative of this. Now I got to do the derivative of this, which I've already done. That's right here. The derivative was negative x to the negative 2. And so now I'm going to need to simplify that. Notice these are exactly the same, so they'll cancel each other out, which has worked out very nicely. And now I'm just left with this thing here. Okay, so I've got 1 over 1 plus 1 over x, and I'm probably going to want to multiply the numerator and the denominator times an x, so I don't have a fraction within a fraction. So if I take this one times x, I'm going to get x plus 1. Alright, so now when I go to plug in infinity, I am going to have infinity over infinity. And guess what that means? L'Hopital's rule one more time. But luckily this is an easy one. If I take the derivative of my numerator and my denominator, I end up with what? The derivative, so now I'm doing the limit as x goes to infinity for the derivative of this. And the derivative of that would just be 1 over 1. And the limit of a constant is itself. So that all comes out to be 1. Now remember, I went back here at this point and I left the e out. I could have went through and had a base of e on every single one of these all the way through, but to make the problem look easier or not have to mess with this e every time, I left it off. So now I got to go back and incorporate it in. So my answer is e to the 1, which is simply e. So the limit of this function right here is e. Alright, one more of those and then we'll be done. Okay, so here's our last example, and notice we have another one of those, x in the base, x in the exponent. So if I were to plug in 0, I would have sine of 0 to the 0 power, and sine of 0 means what's the y value at 0 radians or 0 degrees? The y value would be 0. So I end up with 0 to the 0. which is one of our indeterminate forms. So I have to do something to try and get this thing in a format where I can use L'Hopital's rule. So to do that, I'm going to do that e to the ln thing again. So I'm going to have the limit as x approaches 0 from the right-hand side of e to the ln of sine x to the x power. And so now I'm going to take that x and move it out in front. So if I do that, I'm going to have x ln sine x. And so now, once again, I'm going to ignore this e and just bring it back whenever I do my answer. So now I'm ready to plug in 0 and see what happens. If I plug in 0 to this, what will I get? I will have 0 times ln of 0. Which, remember, we're just doing this as x approaches 0. So if you imagine that x never actually got to 0, so sine of 0 is 0, but then you have ln of a number that's in crazy large, so that's basically going to come out to be an infinity, and you're going to end up with a 0 times infinity. Once again, undetermined form. And you can probably just see that when you're going to look at this and go, clearly this is not going to set up for L'Hopital's rule. So since we can just look at it and see, hey, that's not going to set up for L'Hopital's rule, why don't we just off the bat, don't even mess with plugging that in and move that x down here like that, so that now I'm dealing with this problem instead of one that I know isn't going to work. Okay, so now I am set up so that I can test it for L'Hopital's rule. Now if I plug in 0, obviously I'm getting 1 over a million, or 1 over a trillion, or 1 over the biggest number in the world. That's going to approach 0. And essentially the same thing happens on this one too. As you approach, the sine of 0 is 0, and think about the logarithmic function. Here's the logarithmic function. As you approach 0, it goes to negative infinity. And I told you wrong on this one. I apologize. If you think about that's a reciprocal function. This is a reciprocal function. As x is approaching 0, if you're approaching 0, you're going to go to infinity. And it doesn't matter. Positives and negatives don't matter on this. As long as you get an infinity on the top and the bottom, you're allowed to use L'Hopital's rule. So once again, we plugged this one, reciprocal function, the 0 into the ln function here. Alright, so now I can use L'Hopital's rule, which says take the derivative of the numerator and the denominator. So the derivative of my numerator, the derivative of an ln, is 1 over that function times the derivative of that function, which would be a cosine. And then the derivative of 1 over x is my x to the negative 1, so I use the power rule and end up with negative x to the negative 2. So now, if you want to simplify that, you could think about this as a tangent on the numerator if you wanted. So think about this as if it were, I guess that would be a cotangent, wouldn't it? So let's go ahead and just work this out here. Cosine x over sine x, and this would be the same as negative 1 over x squared if you shoved your x squared. So then if I flip and multiply, I'm going to get that. Which is equal to x squared times the cosine of x over the sine of x. Alright, now if you think of cosine over sine, that would be the same thing as a cotangent. And cotangent is equivalent to 1 over tangent. Because we'd probably rather work a tangent than a cotangent. So just switching cotangent to 1 over tangent, cosine over sine to cotangent. All right, so now if you plug in 0, what happens? What's the tangent of 0? Tangent of 0 means what's the slope at 0 degrees? Slope at 0, 0. So there we go. Now I've got another L'Hopital's rule to do. You can see we have to do it twice a lot. So I get to take the derivative again. The derivative of an x squared is a 2x. And if you remember, the derivative of tangent is secant squared. So now we're ready to do the limit as x approaches 0. And so you could, instead of dealing with a secant on the bottom is the same thing as a cosine on the top. And so now if I plug in 0, I get 2 times 0. Cosine of 0 is 1, so I get a 1 squared. And 0 times anything is 0. So my answer comes out to be 0. But remember, what did I do in the very beginning? I had that e that I threw out. Remember this thing right here? I had thrown it out at this point, so now I've got to bring it back. I've really got e to the 0, and anything to the 0 power is 1. So the final answer is a 1, not a 0. And that's your last example. Problems will be posted in Schoology.